Assalamu alaikum students. Now we are starting our next chapter, lenses. Here in this chapter we will study about both the lenses, both convex and concave lenses. Lens actually is a curved piece of transparent material. It's made up of glass or plastic or any curved transparent material behaves like a lens. Even a water droplet also behaves like a lens. So thin lens is an optical system with two refracting surfaces. There are two surfaces which will cause refraction of the light. Okay, and the path of the ray of light changes. The simplest lens has two spherical surfaces close enough together that we can neglect the distance between them. So the thickness of the lens can be neglected. Okay, so thin lens and a thick lens, there will be difference in the performance due to certain reasons. Okay, so with that difference we will study later. Lens can be converging or diverging. Converging lens is also known as convex lens, and diverging lens is also known as concave lens. Converging lens or convex lens has the property that when a beam of light ray parallel to the axis passes through the lens, the rays converge to a point f2 and form a real image at that point. A positive lens, f1 and f2 are both positive. Okay, it means a convex lens has real principal foci, the focal point, the point where parallel rays of light get focus are real. Here there is a detailed diagram. So this is a lens and these are the parallel rays of light. And these parallel of rays of light, after passing through the lens, they converge. They meet at a point. So this point is called principal focus or focal point. So since the rays are really coming and converging at this point, so this principal focus is a real principal focus. In the same way, there is another principal focus on this side. So these rays coming from the left side, they get focus on the right side. In the same way, the rays which come parallel to each other from the right side will get focus on the left side. Okay, so this distance between the center of the lens, this is the center of the lens, and we also call it optical center. So optical center and f1 is called focal length. So this is also a focal length. So converging lens has a real focal point and real focal length. Okay, so two principal of foci are there, and optical center is the center of the lens. And here the rays are coming from the optical center, the not optical center, from the principal focus. So these rays after passing through the lens will become parallel. Okay, and the same way the rays which are parallel to each other, the path will be reversed. Parallel rays will come towards the focal point. These are the two lenses shown again, converging and diverging, and this is bio-convex lens. Both the surfaces are convex, and this is bio-concave, means both the surfaces are concave. They have depth, and this is curved outward. Convex lens has the surface bulging outward, and concave lens has surface which is curved inwards. It has depression or depth. Principal axis, the line which joins optical center of the lens and the two principal of foci. Every lens has two principal of foci, one on this side and on the other one on the other side. So this line which is passing through the center of the lens is principal axis. Diverging lens or concave lens, the beam of parallel rays incident on this lens diverges after refraction. See, this converging of the rays and diverging of the rays is due to the refraction. And this is a negative lens because its principal of foci are not real. Okay, the rays actually do not pass through the focal point. We will see it in the next diagram here. These are the parallel rays, and they, instead of converging towards this f1, they are diverging. This ray is going this way, the ray which is striking the center is going straight, this ray is diverging in this direction, this ray is diverging in this direction, and they are, when we produce these lines backward, they appear to be originating from this f2. Okay, so actually they are not coming from this point, they just appear to be coming. So that is why it is virtual principle of foci. Okay, one on this side and the other one on this side. It means the rays which are parallel to each other and come from the right side of the lens, they will scatter or diverge in this direction. Okay, and the a point from which they appear to be coming will be on this side. Okay, this will be reversed. See here. So, and in the same way, reverse may happen. The rays which are apparently coming towards the optical center, they become parallel to the principal axis. Ray coming, we will see the previous diagram back. The rays which are parallel, they diverge, and the rays which are coming towards the principal focus f1 on this other side, they become parallel. Okay, if they are seen to be hitting the optical center principal focus, they will become parallel. Parallel rays will appear to be coming from this point, and those rays which are striking this optical center on the other side, appear to be striking on the other side, become parallel. Okay, so converging lens thicker in the middle and thinner at the edges, and diverging lens thinner in the middle and thicker at the edges. There are some types of lenses here. This is having one side concave and the other side convex. Okay, and this is one side plane and the other side convex. So we also call it plano-convex. This is double convex, and this has again one side convex and other side concave. So meniscus, these two are meniscus. Okay, and this is diverging lens, but this is plano concave because one side is plane straight and the other side is curved inward. Okay, this is plano convex, has other side curved outward. Okay, and this is double concave lens, both the sides are curved inwards. There is a difference between curved mirrors and lenses. Curved mirrors is not in the syllabus of CAIE, but lenses are there. The concave has negative focal length and it forms virtual image. Okay, and convex lens has a positive focal length and it forms real or virtual image depending on the position of the object. Here, how the images are formed by lens. Okay, so lens, if the image is real, it will be inverted. See, it's upside down, but it's real image can be obtained on the screen. Okay, and this is formed due to the rays actually meeting each other. Okay, so these are the rays of light, they are passed through the lens and they pass this parallel ray, the ray which is parallel to the principal axis is passing through f, and it is meeting the point where they are meeting, is forming the image. Okay, the image is formed at that point. Okay, this is just a ray diagram. We will study detail of this, how the rays are to be drawn. And see, this is the lens in between, this is an object, illuminated object. Okay, the object on which the light is falling, so the image can be formed on the other side. Okay, real image will be formed on the other side and it will be inverted. And what is the position of the image? That depends on the position of the object. How to draw the ray diagram? A ray diagram is best way to understand the type of image that is formed by a lens. Okay, so whether the image is real, virtual, magnified, or diminished. okay, upright or inverted. Okay, so there are three, these are the rules which are to be followed in all ray diagrams. There are three types of basic rays. See, the ray that passes through the center of the lens is not deflected at all, it will go straight. And the ray of light parallel to the axis passes through the far focal point. A ray passing through the near focal point emerges parallel to the principal axis. Okay, let's see a better diagram of this. This is the ray which comes parallel to the principal axis. This line is central line which is joining F and F on the two sides. Okay, F and F, principal focus or focal point, and this is the center of the lens. We call it optical center. The line which joins these two is principal axis. So the first ray which is coming parallel to the principal axis, it passes through F on the other side. See, the ray of light uh, parallel to the principal axis passes through the far focal point B. Okay, so this is passing through this point. And the ray, first one, the ray which passes through the center of the lens does not deflect. This one, the ray which strikes the optical center goes undeviated. The green color ray, second ray, is going undeviated. Let's see what is written about the third one. A ray of light passing through the near focal point emerges parallel to the principal axis. This third ray, which passes through this first focal point, it becomes parallel. Okay, the one which comes parallel, it passes through the focal point on the other side, and the ray which strikes the lens and comes towards the lens through this principal focus, it becomes parallel. Okay, and this is the same like diagram is drawn for the concave lens, and it is bit different. And here we will study in detail about it afterwards. First, let us see it again about the convex lens. We will draw the ray diagram here. Three lenses are shown here. So this is the convex lens, and this is F1 and F2 on the other side. Okay, so first ray which comes parallel to the principal axis, this is the ray. This line, central line, is already drawn, the one which is parallel to the principal axis. What happens to this ray? After passing through the lens, it will pass through F2 on the other side, means it will go this way. Arrow has to be drawn to show the path taken by ray of light. Second ray, this was the first ray. Any ray can be called first. Okay. Second ray, which strikes the optical center, it goes undeviated. What does that mean? This the ray may be going this way. This, it is striking optical center, so it does not deviate. Goes straight. Okay, in the same way, we have to put an arrow showing the direction of the ray of light. The ray coming this way, it will go this way. Okay, so I can draw direction. The ray may come along the principal axis also. A ray may come along this line also. It will go undeviated. So I have shown here three rays. Striking horizontally. Horizontally, it is coming towards the lens. So these are the three rays striking the mirror, and none of them is deflected. Okay. Now third ray, the ray which comes towards the lens through F on one side will become parallel to the principal axis on the other side. What does that mean? It is coming towards the lens through this F. Okay, so what will happen to this ray? It will become parallel to the principal axis. This is principal axis, and ray is becoming parallel. So we need to choose any two rays to locate the image formed by any object. Let us come back to this. Okay, so here this is an object placed at a point, okay, and its image is formed on the other side. Okay, and all three rays are drawn. It's not necessary to draw all three rays. Any two rays will be sufficient to locate the image. The point where the two rays intersect each other will be the position where image is formed. This was about the convex lens, and this image is real image, an inverted image. Okay, and the concave lens, it always forms virtual image. Here again it's about the rays. Third ray that is coming towards the first focal point, it emerges parallel to the principal axis. I have already explained in detail about it. Let us see the concave lens. Okay, so again the simple diagram, more clear. First, second, third. First ray parallel to the principal axis going this way. This is going undeviated, and this is striking the lens through the. It comes through the principal focus on this side. It will be parallel after passing through the lens. Now concave lens. See, this is the ray of light, and it parallel ray. It will scatter, and it appears to be coming on the from a point which is virtual focal point of the concave lens here on this side. Okay, this is the point on this side because the ray appears to be coming. When we elongate this path, we produce it backwards. So this is the point where it's striking on the line of principal axis. This is the line of principal axis. Okay, the definition of principal axis is the same for both concave and convex lens. Okay, and this is the ray, second ray, which goes towards the optical center. Concave lens also has an optical center. Okay, this is center of the lens, so that goes undeviated. Okay, it does not deflect. And this is the third ray, which appears to be striking F on the other side. Okay, the one which appears to be striking F on the other side will become parallel to the principal axis. Okay, and the ray which is coming parallel to the principal axis on this left hand side, it will scatter, it will deflect in such a way that it appears to be coming from the principal focus on this side. So in none of the principal focus the ray is actually going. See, the dotted line is shown here, dotted line is shown here. That is why it is virtual principal focus. Now this is the image formation. The image is real depending on the position of the object. Okay, so if the object is placed beyond principal focus, the image will be real. Okay, so here this is principal focus f1 and object is placed beyond it. Okay, so this one ray, it's going through f2, and other ray which is going through the optical center. So the point where these rays intersect each other will be the point of image formation, where the image will be formed. So here the image is real, inverted, and smaller, diminished. We call it diminished. Okay. In the second diagram, the ray object is brought slightly close. Okay, so this object is brought slightly closer, so image is moved away from it. Okay, and the image size has increased. Here object was like at greater distance, so image was smaller. Okay, here the image is of the same size. Okay, so this position will definitely be 2f. Okay, let me tell you what f and 2f are. This is the first ray going parallel to the principal axis. I will redraw it for you here. I will delete all these things, unnecessary things. Okay, so this is f1. F1 and f2 will be at the same distance from the lens. If this is 2 centimeter, this will also be 2 centimeter from the lens. This is focal length. Focal length is measured in meter or centimeter. Okay, so I will just elongate this line so that I can show UF and 2F. Okay, if this one is F1 and it is at suppose 4 centimeter, so this is F, we label it F. Okay, so if this is 4 centimeter, means there will be another point 2F on this side. So what will be its distance? 2 times this 4 means 8 centimeter from the optical center. In the same way, there will be 2F2. Okay, so the ray which suppose we have object beyond 2F. We have placed an object which is beyond 2F. So this is your object placed here. Okay, and this is the tip, it means upper part of the object. So we will take 2 rays, one ray from the top of the object, okay, so it will pass through F and I have to elongate this ray. Now I'll take one more ray, one ray coming parallel to the principal axis, it will go through F2 on the other side, okay, and another ray. So the point where it is striking is here. So this is slightly slipped, okay, anyhow. I will redraw. Now this is the point of intersection. It means image forms here at this point. At which point? Here. And see since the top is the ray coming from the top appears at the bottom. Okay, they intersect at the bottom. Here, it means the bottom, the image is inverted. The bottom will appear here. Bottom will appear here and top will appear at this point. Okay, so the image is real, inverted. It is smaller than the object, so we call it diminished. forms between f and 2f on the other side. Okay, so this was about this object when it is placed beyond 2f. What happens when the object is placed between exactly at 2f? If the object is placed exactly at 2f, so what will happen to the ray of light? Optical center, this principal axis. Okay, this is f1 and this is 2f1 at the same distance. Okay, this 4 centimeter is 4 centimeter. F2 will also be 4 centimeter. It is 2f. Okay, now we are placing object at 2f. We have brought little closer. So when object is at 2f, how will the image form? One ray coming from the top of the object, it is going through f2 on the other side, and I have to elongate this ray. Okay, other ray which comes from here, it will go undepleted. Okay, so image forms exactly at 2s because they are intersecting at this point. And my measurement, of course, are not very accurate. So anyhow, this is the position where the rays are intersecting. So inverted, object at 2s. What about image? Real. If you place paper as a screen here on this side, that image will appear on the real. Inverted, same size as that of object. Okay, so these are the characteristics of the rays. So if object is at 2f and forms at 2f on the other side. Okay, so here two diagrams were shown. So if you keep on bringing the object close, what will happen? Image will keep on shifting away. Let us draw one more diagram. What if the object is placed between f and 2f? So this is your 2f, 2f, 2, this is 2f1, and object is placed somewhere here. So the ray coming parallel to the principal axis, this is principal axis, I already told. Okay, so this ray is going this way. Let me elongate this ray because we don't know where the two rays will be meeting. Okay, so the ray which comes towards optical center, should have made this little longer. Okay, so this is the point where the two rays are meeting. I have to elongate optical center. The image is formed here. So what do you say about the image? It is bigger than the object. We call it magnified. Inverted, real, and forms beyond 2f. This is image, this is object. Object between f and 2f. Okay, this is 2f and this f. Image forms beyond 2f, real, inverted, and magnified. What happens when we place object at f? If you place the object at f, the rays will become parallel to each other and the image will be formed at infinity. You can see this object is at f, the image, the rays after passing through the lens have become parallel to each other. It means at very long distance they will be meeting. It means image forms at infinity. When the object is at f on this side, image forms on the other side at infinite distance. Now we we are bringing object closer to the lens. So now first it was beyond 2f, then at 2f, then between f and 2f, then f, now between optical center and f, this one. So here the optical center, this is object, and the ray which is parallel to the principal axis, it goes through f2 on the other side, and the ray which strikes the optical center goes undeviated. It means they are going away from each other. When you elongate, they don't appear to be meeting any like on this side at all. Okay, it means when you produce them backward, they appear to be coming from this point. Since the rays are not coming from this point, the image is virtual, upright, and magnified image. The magnifying glass, which you use to see the bigger object, bigger paper, something which is written very small on the paper, you use magnifying glass. So this is a magnifying glass. Okay, so image forms on the same side where the object is. See, object is on the left side, image is also formed on the left side, virtual and magnified image. One more series of diagrams. See, this is the child standing beyond 2f, image forms between f and 2f, inverted real image. Okay, object at 2f, image is also at 2f, on the other side same size as that of the object, real and inverted. Object between 2f and f, between f and 2f, he has come closer, the child has come closer, image has shifted away from 2f, magnified. See, image is bigger than the object. Object between f and 2f, image is real, inverted, and magnified image. An object has further close between optical center and focal point. This is the object. See, the image is virtual. Okay, it cannot be obtained on the screen. Okay, you can just see on from this side of the lens. Okay, if you place a paper, you won't be able to obtain it. But in the other, this case, if you place a screen like any piece of cloth, curtain, paper, the image will be formed. Okay, so this is a virtual image, magnified image. And this is the formula. How much magnified? We have a formula, image height over object height. We measure the height in centimeter, okay, and we can measure the magnification. It's a ratio of height of the image and the object. It can also be obtained from the other formula, image distance divided by object distance. Okay, magnification also depends upon this thing, image distance over object distance also. V image height, U object height. V image distance, U object distance. Okay, so you can say image height is upon object height is equal to image distance over object distance. So these are the diagrams, and let us stop our lesson here, and we will okay, we'll study one more thing, finding a focal length. If you want to find the focal length, what will you do? You will from a distant object, the rays from the distant object are almost parallel to each other. Okay, you will place it near a window and try to get the image of the distant object so that the rays are almost parallel, and parallel rays, they will converge and they will meet at a focal point. So here you will place a piece of paper and see the image of these things will be obtained, inverted and real image will be formed on this paper. So this distance between the paper, which is serving as a screen, and the lens will be giving you the approximate focal length. Okay, so you place a ruler between them and the parallel rays which are coming from the object, distant object, and they are converging at f. Okay, so that f and optical center, the distance between the 2 points will give you focal length. Okay, so that's all for today. Watch this video carefully and watch it again if any point is not clear, and let me know.